Welcome back to the deep dive. Today, we're cutting through the noise, going to get you really well informed about two reactions that are, well, absolutely fundamental if you want to understand organic chemistry.
That's right. Substitution and elimination reactions.
Exactly. You'll bump into countless reactions in this field, but these two are kind of special.
They really are.
Yeah.
So widely applicable, so versatile.
Mastering them feels like, I don't know, gaining a superpower for building organic molecules.
It really does unlock a lot.
Okay, so let's unpack this. We're diving deep into Chapter 12 from Organic Chemistry I for Dummies, seconded. That's our main source today.
Yep, and it promises to demystify these core ideas.
Right, from the basic principles and mechanisms all the way down to how you can actually predict what's going to happen in the flask.
That's the goal.
Yeah.
Our mission today is really to pull out the most crucial insights, the practical stuff.
So you don't just grasp what these reactions are, but why they act the way they do.
Exactly. And how you can spot them. Try to cut through the jargon, focus on explanations that just click.
Get those aha moments without feeling buried in detail.
Hopefully. Think of it like this. Substitution. One group on a molecule just swaps out for another. Simple swap.
Okay.
And we'll look in two main ways that swap happens, SN1 and SN2 mechanisms.
SN1 and SN2. Got it. You had that relationship analogy.
Yeah. So SN2 is like quickly ending one relationship and immediately starting a new exclusive one. Bam. Done.
Quick swap.
Right. Whereas SN1 is more like a breakup than a period of being single, independent, and then maybe forming a new attachment later on.
That helps visualize it. So with these substitution group swaps, how do we even start to predict which way it'll go, SN1 or SN2? What are the clues?
The million-dollar question. And like so often in organic chemistry, the answer is, well, it depends.
Of course it does.
It really hinges on a few key things, like the solvent you use, the actual molecule that's changing. We call that the substrate.
The substrate, right.
And the substituting group itself, the incoming group, that's our nucleophile. Literally nucleus lover.
Nucleus lover. Okay, let's break those down. Where should we start? SN2.
Yeah, let's start with SN2. Stands for substitution nucleophilic bimolecular.
Bimolecular. Why that?
Because it all happens in one single concerted step. Everything at once.
Synchronized.
Exactly. Your nucleophile, that electron-rich species that loves positive nuclei, attacks a carbon atom.
Okay.
And that carbon is attached to what we call a leaving group, usually shown as X, something that's, well, ready to leave.
Makes sense.
So at the exact same moment the nucleophile attacks, it pushes out, kind of gives the leaving group the boot.
Kicks it out.
Yeah, and takes its place. It's this perfectly timed molecular dance.
Why does that happen? What's the attraction?
It's all about charge. That bond between the carbon and the leaving group, it's polarized.
Meaning?
The leaving group is usually electronegative, so it pulls electron density away from the carbon.
Leaving the carbon a bit positive.
Exactly, a partial positive charge. So the nucleophile, which is electron-rich, is naturally drawn to that electron-poor, partially positive carbon.
The classic rich meets poor story of electrons.
You could say that. And this fundamental attraction, electron-rich nucleophile, seeking an electron-poor electrophile, that's a species that loves electrons. That's key to understanding tons of organic reactions.
Okay, that makes sense. So the single-step SN2 dance, how fast does it happen? What controls the speed?
Well, the Fatchin 2 and SN2, that points directly to the rate equation.
Which is?
Rate is substrate nucleophile.
So the speed depends on both the concentration of the substrate and the nucleophile.
Precisely. Yeah. Making it a second-order reaction.
Yeah.
Double the substrate, double the rate. Double the nucleophile, double the rate.
Okay. And the energy. You mentioned a single step.
Right. Imagine climbing a single energy hill. Just one activation barrier to get over.
Okay.
The very top of that hill, that's the transition state. It's this super fleeting high-energy moment.
Not something you can actually isolate.
No, not at all. It's just that point where the old bond is partially breaking and the new one is partially forming. A snapshot in time.
Got it. So we have the nucleophile attacking the carbon, but what about the molecule itself? Does the shape of the substrate matter? You hear about steric hindrance?
Oh, absolutely crucial. Your analogy earlier about a fan trying to get an autograph.
Yeah.
That's perfect. The R groups on the carbon, those other atoms or chains attached to it, they act just like bodyguards.
Bodyguards, so they physically get in the way.
Exactly. They hinder the nucleophile's approach, block the path.
So the more R groups, the more bodyguards, the harder it is for the nucleophile to reach that carbon.
You got it. SN2 reactions work best, fastest, with methyl substrates, no bodyguards at all.
Okay.
On primary substrates, just one bodyguard. They're still pretty accessible.
Secondary. 2 bodyguards.
Slower, much slower. The path is getting crowded.
And tertiary, 3 bodyguards.
Usually. No dice for SN2. Forget it. They completely block the backside attack needed for SN2. That physical blocking, that steric hindrance.
Okay.
And because the nucleophile has to attack from the back.
If the back is blocked, reaction fails.
Pretty much. Which is actually really useful information if you're planning a synthesis.
Okay, so steric hindrance is big. And since the nucleophile's concentration is in the rate equation, you obviously need a good nucleophile. What makes one good?
Right. A potent nucleophiles is key for SN2. Basically, anything with a lone pair of electrons can be a nucleophile.
But some are better than others.
Definitely. Now, nucleophilicity, its knack for attacking carbon, often goes hand in hand with basicity, its knack for grabbing a proton. But they're not exactly the same thing.
Example.
Okay, take methoxide, CH3O.
Yeah.
Good nucleophile. Now take t-butoxide, CH3CO. It's a really strong base, but it's actually a poor nucleophile.
Why?
It's a big hindrance again. Those 3 bulky methyl groups on t-butoxide make it too big and clumsy to effectively attack a carbon, even though it's great at grabbing protons.
Ah, okay. Any general rules for nucleophile strength?
Yeah, a couple of good rules of thumb. Negatively charged ones are usually stronger than their neutral versions, like OH is stronger than H2O.
Makes sense. More electron density.
Right. And interestingly, nucleophilicity generally increases as you go down a column in the periodic table.
Count. Why is that?
Larger atoms are more polarizable. Their electron clouds are kind of bigger and squishier, easier to distort to form that bond. So like H2S is a better nucleophile than H2O. And iodide is better than bromide, Br.
Okay, interesting. What about the 3D shape? The stereochemistry. You said backside attack. What does that do to the molecule?
This is one of the coolest, most defining features of SN2. That backside attack forces the groups on the carbon to flip over.
Like the umbrella in the wind.
Exactly. It inverts the configuration. We call it inversion of stereochemistry.
So if you start with one specific 3D arrangement, say S configuration,
Your product will often have the opposite R configuration. It's a complete flip.
that's not just a minor detail, is it?
Not at all. Think about pharmaceuticals. A molecule's exact 3D shape can mean the difference between a life-saving drug and something useless or even harmful.
Wow.
So knowing that SN2 guarantees this specific inversion, that's incredibly powerful for designing molecules precisely.
Critical. Okay, does the solvent, what everything's dissolved in, affect SN2 as well?
Oh, hugely. SN2 reactions really prefer polar aprotic solvents.
Polar aprotic, meaning
Okay, polar means the solvent molecules has charge separation, which helps dissolve things. Aprotic means they don't have OH or NH bonds. Think DMSO or acetone or ethers.
why aprotic? What's wrong with protic solvents like water or alcohol?
Protic solvents, those ones with OH or NH bonds, can form hydrogen bonds with the nucleophile. They surround it, forming a solvent cage.
Like trapping it.
Sort of. It stabilizes the nucleophile too much, makes it less reactive, less naked, and ready to attack. Polar aprotic solvents dissolve everything but leave the nucleophile more free and energetic.
Okay, so polar aprotic for SN2. And one last piece for SN2. The leaving group. It needs to be a good leaving group.
Absolutely essential. You need a group that's stable on its own once it leaves, taking its electron pair with it.
Stable how?
Now think of it this way. The best leaving groups are very weak bases. They're happy to exist independently.
Weak bases, like the conjugates of strong acids.
Exactly. That's why halides iodide, bromide, chloride are great leaving groups. They come from strong acids like HI, HBr, HCl. Tosylate is another fantastic one.
And bad leaving groups.
Strong bases. Things like hydroxide, OH, alkoxides, RO, the amide ion, NH2. They are not stable on their own. They're too reactive.
They just won't leave.
They really don't want to.
Yeah.
That's why you generally won't see SN2 happen directly on, say, an alcohol or an ether. Their leaving groups, OH or RO, are terrible. You have to convert them into something better first.
Got it. Okay, that's a deep dive into SN2. Now, if SN2 is the quick concerted swap, what about SN1? Your stay single for a while analogy.
Perfect transition, yeah. SN1 is fundamentally different. It's a two-step process.
Same steps. Okay.
Step 1, the leaving group just leaves, packs its bags, takes off all by itself.
Without the nucleophile pushing it.
Exactly. It leaves behind a carbon atom with a positive charge. We call this a carbocation intermediate.
Carbocation. Okay.
And this first step, the leaving group departing, that's the slow step, the rate-determining step. It's the bottleneck for the whole reaction.
Like the tiny washing machine in your laundry analogy from before.
Precisely.
Mm-hmm.
Then, step 2, after the carbocation is formed, the nucleophile comes in and attacks that positive carbon to make the final product.
So if the carbocation formation is the slow bottleneck, How does that change the rate equation compared to SN2?
Big difference. The rate for SN1 is just rate yields case substrate.
Whoa, the nucleophile isn't even in there?
Nope, because it only gets involved after the slow step. The reaction can only go as fast as that first step, the leaving group leaving.
So making the nucleophile stronger or adding more of it doesn't speed up SN1.
Doesn't help at all. It's like getting a faster dryer when your washing machine is already slow. The overall laundry time is still limited by the washer.
That makes perfect sense. So what kinds of substrates like to do SN1 if SN2 likes less bulky ones?
SN1 is the opposite. It needs substrates that can form a stable carbocation when the leaving group leaves.
Stable carbocation, what makes one stable?
More alkyl groups attached to that positive carbon help stabilize it. Think electron donation. Also, resonance really helps.
Resonance, spreading the charge out.
Exactly. Spreading that positive charge over multiple atoms makes the carbocation much more stable, easier to form.
So which substrates are best?
Tertiary substrates are the best for SN1, 3 alkyl groups stabilizing that carbocation. Then secondary,
Primary.
generally 2 unstable. Primary carbocations are really hard to form. But benzylic and allylic substrates are also great for SN1.
Why them?
Resonance. They have double bonds nearby that can share the positive charge, stabilizing the carbocation significantly.
Okay, tertiary, secondary, benzylic, allylic. Got it. How about solvents for SN1? If SN2 likes polar protic.
SN1 prefers polar protic solvents.
The opposite again, like water or alcohols. Why?
Yes. Those protic solvents are crucial for stabilizing that positively charged carbocation intermediate formed in the first step.
How do they stabilize it?
Through interactions like hydrogen bonding. They kind of surround and cushion the positive charge, lowering its energy.
And lowering the energy of the intermediate helps the first step happen faster.
Exactly. It lowers the energy of the rate-determining step's transition state, speeding up the whole reaction. The nucleophile being slightly caged isn't an issue here because its speed doesn't matter for the rate.
Okay, huge difference there. What about stereochemistry? SN2 gives that clean inversion.
Another major difference. Remember that carbocation intermediate in SN1?
Yeah, the flat one.
It's sp2 hybridized, meaning it's planar, flat like a pancake.
Okay.
So the incoming nucleophile can attack that flat carbocation from either the top face or the bottom face.
with equal chance.
Pretty much, yeah. Roughly equal probability. And what does that lead to?
A mix.
A mix, specifically a racemic mixture, usually close to a 50-50 blend of the two enantiomers.
Enantiomers.
Huh?
The non-superimposable mirror images, like left and right hand.
Exactly. So unlike SN2's clean inversion, SN1 scrambles the stereochemistry. You lose that specific 3D starting information.
Big difference. Any other quick notes on SN1 we should keep in mind?
Yeah, just a couple. SN1 reactions generally work fine, even best, with weak nucleophiles, because nucleophile strength doesn't drive the rate.
Okay.
Like SN2, you still absolutely need a good leaving group. That first step won't happen otherwise.
Right.
And one more thing, remember carbocations. They can be mischievous little devils.
Mischievous.
They can undergo rearrangements. If the positive charge can shift to an adjacent atom and become more stable, like going from secondary to tertiary, it often will.
Spontaneously.
Yep, before the nucleophile attacks, which means you might end up with a product structure you totally didn't expect. Something to watch out for in SN1.
Definitely sounds mischievous. Okay, this is a ton of detail for SN1 and SN2. Can we just quickly recap the absolute key differences, like a cheat sheet?
Good idea. Let's do a rapid-fire comparison.
Okay. Substrate preference.
SN1, tertiary secondary, loves stability, SN2. Methyl primary secondary, hates crowding, remember. Tertiary, never SN2. Methyl, always SN2.
Rate equation.
SN1, rate case substrate. Only depends on the substrate.
Mm-hmm.
SN2, rate case substrate nucleophile. Depends on both.
Nucleophile role.
SN1, strength doesn't really matter for the rate. Weak is fine. SN2 needs a good, strong nucleophile.
Stereochemistry outcome.
SN1, racemization, mixture of enantiomers. SN2, inversion of configuration, clean flip.
Leaving group.
Both need a good one. Essential for both.
Solvent.
SN1 likes polar protic, water, alcohols. SN2 likes polar protic, DMSO, acetone.
Rearrangements.
SN1, yes.
Yeah.
Carbocation rearrangements are possible. SN2, no rearrangements. Concerted step.
What about that tricky middle ground, secondary substrates?
Ah, yeah, the gray area.
Yeah.
Secondary can potentially do either. You have to look really closely at the other conditions, the solvent, the nucleophile strength, to predict which pathway might win, or if you'll just get a messy mixture of both SN1 and SN2 products.
Okay, that clarifies the substitution world. But you mentioned way back at the start that elimination reactions often compete. What are they about?
Right, eliminations. equally important. Instead of swapping a group, elimination reactions typically involve losing two groups from adjacent atoms in the substrate.
Losing two groups. What usually leaves?
Often it's a hydrogen atom, H from one carbon, and the leaving group, X, from the carbon next to it. Effectively, you're eliminating a molecule of HX.
And what does that form?
It creates a double bond between those two carbon atoms. You form an alkene.
Ah, making double bonds. Okay. And I bet there are different mechanisms, E1 and E2.
You got it. And they have some interesting parallels with SN1 and SN2. Let's start with E2.
Okay, E2. The 2 makes me think. Single step, concerted, like SN2.
Precisely. E2 is a single-step concerted elimination. A strong base comes in.
A base this time, not necessarily a nucleophile.
Often a strong base, yes. It plucks off a proton, H+, from a carbon next to the one with the leaving group. At the same time, electrons shuffle around to form the new double bond between those two carbons, and simultaneously, the leaving group gets kicked out.
All in one go.
All in one go.
Mm-hmm.
There's a key geometric requirement here, though.
Geometry.
Yeah. For E2 to happen efficiently, that hydrogen being removed and the leaving group usually need to be anti-periplanar.
Anti-periplanar, what's that mean?
It means they need to be in the same plane, but pointing in opposite directions across the carbon-carbon bond. Think 180 degrees apart, like one pointing up, the other down on adjacent carbons.
Okay, specific alignment needed, and the rate.
Rate, case base substrate. Second order again, it needs that strong base, and its concentration matters, along with the substrate. E2 is actually the most common way eliminations happen.
Got it. Strong base, anti-periplanar, makes an alkene. That's E2. What about E1?
E1, first order elimination. It's less common, but important. And just like SN1.
It's a two-step process involving a carbocation.
Exactly. Step 1. Leaving group pops off all by itself to form that carbocation intermediate. Same slow rate-determining step as SN1. Okay. Step 2. Then a base comes along, and it can even be a weak base here, and plucks off a proton from a carbon adjacent to the carbocation. Those electrons then swing down to form the double bond.
And the rate equation for E1?
Just rate, say substrate, first order. Because that carbocation formation is the slow step again.
So the base strength doesn't matter for the E1 rate?
Nope. That's why E1 typically happens when you only have weak bases around. They aren't strong enough to force the concerted E2 pathway, so the molecule takes the E1 route if it can form a stable enough carbocation.
Okay, this makes sense, but this is where it gets really confusing, right? You've got SN1 competing with E1 and SN2 competing with E2. How on earth do you predict what's actually going to happen in a reaction flask? This must drive chemists crazy sometimes.
Oh, it's the classic organic chemistry challenge. You've hit the nail on the head. Reactions that are purely substitution or purely elimination, they're actually kind of rare.
Because good nucleophiles are often good bases and vice versa.
Exactly that. They often want to do both things. But there are some really useful generalizations, kind of like a decision tree, that help predict which pathway will likely dominate.
Okay, give us a decision tree. Where do we start?
First, look at your region. Is it strong or weak?
Strong meaning strong base or strong nucleophile?
Yeah, strong bases and or strong nucleophiles. Think hydroxide, OH, alkoxides, or Iger. These tend to push things towards second-order pathways.
So SN2 or E2? Or both?
Often a mixture of both, yeah. They're aggressive. They force a fast, concerted reaction if possible.
Okay. And weak reagents, weak bases nucleophiles.
They usually lead to first-order products, SN1 or E1. They typically wait around for that carbocation to form first.
Okay. Strong forces, second order. Weak allows first order. What's next in the decision tree?
The substrate type. This is huge.
Right. Primary, secondary, tertiary.
Okay. Primary substrates and methyl. They strongly favor SN2. Least hindered easy backside attack.
Mostly SN2.
Yeah.
Any elimination.
You might get a little bit of E2 if you use a really, really strong and bulky base that finds it hard to be a nucleophile. But generally, primary means SN2. Methyl is almost always SN2.
Okay. What about tertiary substrates? The most hindered ones.
Can't do SN2, remember, too crowded. So if you hit a tertiary substrate with a strong base, you'll get E2 elimination almost exclusively.
Makes sense. The base can still grab a proton from the outside.
Right. But if you use a weak base nucleophile with that tertiary substrate, especially in a polyprotic solvent,
then it can form a stable carbocation, leading to SN1 and E1.
Exactly. You'll likely get a mixture of SN1 and E1 products. The conditions favor the first-order pathways.
Okay, which leaves the tricky one. Secondary substrates.
Yes, the battleground. These are the toughest because, theoretically, All four mechanisms, SN1, SN2, E1, E2, are possible. It really depends heavily on the conditions.
So for secondary, what are the general trends?
With weak bases or nucleophiles, especially in protic solvents, you're likely looking at a mixture of E1 and SN1, again, conditions favoring first-order carbocation routes.
And with strong bases or nucleophiles?
Then you're pushing it towards second order. You'll typically get a mixture of E2 and SN2. Which one dominates depends on specifics like how bulky the base is versus how good a nucleophile it is.
Secondary sounds like a real balancing act.
It absolutely is. You have to weigh all the factors carefully.
Are there any aha moments, like specific reagents or situations where you can say with more confidence, okay, this is definitely going to be substitution, or this will be elimination? Any shortcuts?
Yes, definitely. This is where knowing specific reagent types pays off.
Okay.
Think about reagents that are good nucleophiles but terrible bases.
Like what?
The halide ions, iodide, bromide, chloride. Also thiols are SH and their anions, RS. These are pretty good at attacking carbon, nucleophilic, but not very good at pulling off protons, basic.
So if you use those?
Their reactions tend to proceed almost exclusively by substitution, usually SN2 if possible, or maybe SN1 if the substrate demands it. You won't see much elimination.
That's a great shortcut. What about the opposite? Strong base, but lousy nucleophile.
The classic example, the one you absolutely must know, is t-butoxide, that bulky CH3,3CO ion we mentioned earlier.
Right, the sterically hindered one.
It's a very powerful base, great at grabbing protons, but it's way too bulky to be a good nucleophile and attack carbon easily.
So what happens when you use t-butoxide?
It strongly favors E2 elimination. It forces the reaction down the elimination pathway because substitution is just too difficult for it. It's a go-to reagent when you specifically want E2 to happen.
Ah, understanding those specific reagent personalities is key.
It really is. Knowing those exceptions or specialized regions gives you a massive advantage in predicting outcomes and, more importantly, in planning how to make specific molecules in the lab.
Wow. Okay, that was a truly fantastic deep dive into substitution and elimination. We went from just swapping groups to the nitty-gritty of SN1, SN2, energy diagrams, stereochemistry, leaving groups.
Then jumped into E1 and E2, alkene formation, anti-periplanar geometry.
And maybe most critically, how to start untangling that competition between substitution and elimination using clues like reagent strength and substrate type.
Yeah, we saw how one single concerted step like SN2 gives that precise inversion, while a carbocation intermediate in SN1 or E1 opens the door to racemization and those pesky rearrangements.
And how tweaking the base, the nucleophile, the substrate really dictates the whole molecular dance.
Exactly, and if we sort of zoom out, understanding these mechanisms isn't just about passing an exam or memorizing rules.
No.
It's about building intuition, developing a feel for how organic molecules behave, how they react and transform based on their structure and environment.
That ability to predict based on subtle changes, that's really the heart of making new molecules, isn't it? Organic synthesis.
That's exactly it. It's the foundation of molecular design.
Which brings up a great question for you, the listener. Now that you have this better toolkit, this deeper understanding of these really foundational reactions,
Right.
what new molecules, what new transformations can you start to imagine?
Yeah. It's a huge playground of chemical possibilities out there.
It really is. Well, thank you so much for joining us on this deep dive today. We really hope you feel not just more informed, but actually more curious to keep exploring.
It's always a pleasure to be your guide on these learning journeys. Thank you for being part of our deep dive family.